Hello, welcome to Chapter 6, Discrete and Continuous Distributions, the Binomial and Normal Models. In Chapter 5, we introduced the classical definition of probability. According to this definition, the probability is always a fraction. In this Chapter 6, we will use this classical definition to build the binomial distribution, and we will also introduce a new concept of probability that applies to continuous variables. With this new concept, the probability is no longer a fraction, but an integral. But don't panic, you will never be expected to calculate the integral manually. A software will do it for you. In particular, we will work with the normal distribution. The vocabulary for this Chapter 6 includes the distinction between discrete and continuous variables. There are various ways of explaining the difference. Here I include two of the characterizations of each type of variable that I consider particularly professional and useful. A variable is discrete when it takes values in such a way that there exists the concept of next value. Alternatively, a variable is discrete when it is possible to find two values so close each other as to make the existence of a third value in between impossible. A variable is continuous when the opposite is true, when it takes values in such a way that it is not possible to apply the concept of next value. Alternatively, a variable is continuous when, for any given two values of the variable, regardless of how close each other they are, it's always possible to find a third value in between them. I will show how to use this criteria as I solve exercise 1. Identify the following variables as continuous or discrete. The height of a person is continuous. If one person is taller than another, no matter how close they are, you can always find a third person whose height is in between. The length of a person's foot is continuous. If you have 2 feet and one is slightly longer than the other, someone else can have a foot whose length is in between. Shoe size. This is discrete. When you are in a shop trying a shoe and it feels a little small, what do? You ask for the next size. And the next size might be a decimal. Let's say that you are trying the 9 and the next number is the 9.5. The point is that there is the concept of next value and no shoe can have a size between 9 and 9.5. That's why we say that this is a discrete variable. Weight of a car is continuous because if your car weighs this and her car weighs that, the car of a third person could weigh something in between. In general, height, weight, length, duration, volume, time are always continuous. It usually doesn't matter if we talk about a building, a movie, a person, or something else. Number of siblings is discrete. If you have 4 siblings and someone else has 5, there cannot be a third person with a number of siblings between 4 and 5. The grade in your last exam is discrete. This is clear if the grade is a letter, F, D, C, C+, etc. You might not see it so clearly if the letter is a number. Bear in mind that an exam has a limited amount of questions or points that you can get. It may have 215 points. If a person gets 210 points, the next value would be 211. It is certainly possible to conceive two exams that are different but so similar as to make it impossible for a third exam to have a grade in between. Age is an ambiguous variable. The institutional concept of age is discrete because it is a natural number, 20, 21, 22, but you could make a case that age is how old are you, and then it is continuous. If two individuals are born in different moments, there is always room for someone else being born in between. Temperature and speed are continuous. If a body is moving with certain speed, what would the next speed be? There is not such a thing as the next speed. We can add as little velocity as we want. Just in passing, Galileo in the 17th century discussed this concept in detail. He said that when a body drops in free fall, the velocity changes a long time and it changes all the time, continuously. Alternatively, you can see that the speed is continuous because if two bodies have a slightly different speeds, you can always have a body whose speed is in between. The same applies to temperature. If two bodies have different temperatures, you can find another body that is warmer than one but colder than the other. One final thought: don't confuse the variable with the way in which we measure it. We agreed that the speed is continuous, but a speedometer can reflect the speed in a continuous way or in a discrete way. If the speedometer has the classical needle that rises with velocity, this is a continuous reflection, because if you have the needle in two different positions, you could always have it somewhere in between. If the speedometer has a screen that displays numbers up to 2 decimals, this is a discrete representation. If we see the speeds 70.13 and 70.14, we will never see another speed in between, because we are displaying only 2 decimals. If you have understood this distinction between discrete and continuous, let's introduce now a famous discrete probability distribution. Exercise 2. We toss a coin 3 times. Use 2 different procedures to find the probability of getting 2 heads. In this context, 2 means exactly 2. First procedure with the help of the sample space. We did this in chapter 5. If we toss a coin 3 times, we can get any of these 8 outcomes. In these 3 cases, we have exactly 2 heads. Therefore, the probability is 3 out of 8, or approximately 0.375. Second procedure, with the product rule for independent events and the addition rule for mutually exclusive events. We saw these rules in chapter 5. Let's focus in one of the outcomes in which we have 2 heads. Heads, and then tails. Assuming that the 3 tosses are independent, this joint probability equals the product of the marginal probabilities. Now, what's the probability of the first toss being heads? 0.5. The second toss being heads? 0.5. The third toss being tails? 0.5. So here we get 0.125. But this is not the only outcome in which we have 2 heads. The probability of 2 heads equals the probability of heads, tails, or heads, tails, heads, or tails, heads. Since these 3 events are mutually exclusive, this combined probability is the addition of these 3 probabilities. And these 3 probabilities are equal each other because in the 3 of them we have 2 heads and 1 tails. This must equal 3 times the 0.125 that we got before, which is 0.375. Of course, we get the same answer as with the other procedure. Here I usually ask my students, which procedure do you find simpler or nicer, or which one do you prefer? Some prefer the first with the sample space, some prefer the second, which is more algebraic, and some say, it depends. If the sample space is small, I prefer the first. If the sample space is big, I prefer the second. This is the ideal answer. In this chapter, we will mostly use the second procedure because we work with more complex sample spaces. The second procedure is the basis of what we call the binomial model. Let's see this with exercise 3. Here we have 2 new challenges. On one hand, we toss the coin 7 times, so the sample space has 2 to the power of 7 outcomes. This is 128 outcomes, not very friendly. On the other hand, those outcomes are not equally likely because this is a loaded coin. Heads are more likely than tails. So you better forget about using the first procedure. Let's go with the second. Letter A, the probability of 5 heads. Let's focus on this particular outcome. 5 heads in a row and then 2 tails. Assuming that the tosses are independent, this joint probability equals the product of these probabilities. The probability of heads is set to be 0.7, and the probability of tails is set to be 0.3. So here we have 0.7 to the power of 5 times 0.3 to the power of 2. This equals 0.0151. But this is only one of the outcomes in which we have 5 heads. The event 5 heads is the combination of this event together with many others. The question is, how many others? In how many ways can we have 5 heads in a total of 7 trials? This is what we call 7 choose 5, or combinations of 7 elements picking 5 at a time. If you studied combinatorics in an algebra course, great. If you didn't, you can study it now, or you can just get this with the calculator. 7 choose 5 is 21. These 21 outcomes are equally likely because each of them has 5 heads and 2 tails. So the final answer is 21 times what we got before. This is 0.318. Notice that this step is not necessary. I include it here for pedagogical purposes. We work with small particulars and we assemble them. And the idea is that you get a better comprehension of the general formula. It's what we call an inductive pedagogy. We go from some particulars to the general. Let's solve directly the probability of getting 3 heads. In how many ways can I get 3 heads out of a total of 7 trials? 7 choose 3. In each of these outcomes, the probability of heads is 0.7, and we want 3 heads. Also, the probability of tails is 0.3, and we want 4 tails. 7 choose 3 is 35, and when we operate this way, we get 0.0972. The probability of 3 heads had to be smaller than the probability of 5 heads because this is a loaded coin that favors heads, so getting a minority of heads is unlikely. If you have understood these procedures, you are ready to understand the formula. In a binomial model, the probability of certain number of successes equals the number of trials choose the number of successes times the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures. This is the abstraction of what we did in the previous exercises. The parameters of a binomial distribution are the number of trials or repetitions of the activity and the probability of success. And the variable of interest is the number of successes. Be aware that for this model to apply, we need 4 conditions. There must be only 2 outcomes, success or failure. The number of trials must be clearly fixed since the beginning. The probability of success must stay the same along the trials. And the trials must be independent each other. Under these conditions, here you have the formula for the expected value of the number of successes and for the standard deviation of the number of successes. Exercise 4 is an example of classical question. The probability that a bus arrives late to the station is 0.15. There are 6 buses scheduled to arrive to the station this morning. Can we use a binomial model to calculate the probability that more than 4 buses arrive late? The answer is no, because in this scenario the trials are not independent. If 1 or 2 buses arrive late, probably there is something going on with the traffic or the weather or an accident, and this makes the other buses more likely to also arrive late. Remember that 2 events are said to be independent when the occurrence of one does not change the probability of occurrence of the other.